Hi, everyone. Welcome to parallel session 3A. We're going to start with a talk by Noah about gaps for the next generation on gravitational-wave observatories. I'm going to chair this session. We have 12-minute talks and 3 minutes for questions at the end of the talk. I'll probably, flag you when you're like 1 minute short. But I'm going to leave Noah talk us about our guests.
All right, hello and good afternoon to you all. My name is Noah Pearson. I'm a graduate student at Montana State University, and as Eleonora introduced me, I will be talking about one of the challenges that we will face in analyzing LISA data in the years to come. So LISA, like any other detector, will not be perfect, and one of those imperfections will be in the form of data gaps that we will receive in the data. These are going to be caused by a variety of reasons, both instrumental and environmental, like micrometeoroid collisions, readjusting mirrors, repointing lasers, etc. And through this variety of causes, we will get quite a diversity in the characters and qualities of gaps. They might be actual, like, total loss of information, or they might be simply just elevated noise or uncharacterized noise, and we might just opt to excise and say this is useless data, we're just going to cut it out and create gaps that way. They will both be long and short in duration, lasting from order seconds to order days, and they will both be scheduled like maintenance gaps, so we know when they're coming, and they will also just be entirely random. And the cumulative effect of all of these gaps could potentially reduce the mission duty cycle down to 80%. Now, that is probably a conservative estimate. This comes from the LISA Red Book. But of course, as diligent data scientists, we want to be prepared for the worst case scenario. And of course, the primary issues that these gaps represent is just information loss, but there's nothing that we can do about that. And ordinarily, if we just continue to work in the native time domain that we receive the data in, these gaps would present no issue because we could just skip over them in the likelihood. But as we all know from analyzing LIGO data, working in the time domain is prohibitively costly. So rather, we should consider an alternate domain to work in. And given the kind of signals that we will be seeing in LISA, these are not like short ephemeral signals that we see in LIGO. We will be seeing signals lasting from months to years. And you can expect that over that long time span, the noise that is in LISA is not going to be stable over that period. And given, due to the fact that we have this unresolved population of galactic binaries coming from the core of the Milky Way, as LISA's antenna pattern is sweeping across it, there will be this undulation in the noise levels. So the noise is going to be highly non-stationary, which means that if we chose to work in the standard Fourier domain, the noise covariance matrix will be non-diagonal and gives a very costly likelihood. So we make the choice to work in this new basis in the time frequency domain using the Wilson-Derbyshire family of wavelets. This gives us many benefits. For one, we get to keep the fast likelihood because the noise covariance is diagonal. And we also have FFT-like transforms that makes it very efficient to move the data from the time domain to this new wavelet basis. But because now we're working outside the time domain, gaps are now trouble. Namely, they produce special leakage, which you're all familiar with in the Fourier domain. There's an analogous version in this wavelet space. So plotted here on the right is just a wavelet reconstruction of a gap sinusoid. So we have this dilution of power vertically in the frequency axis. And so if we don't do anything to manage this special leakage, then we're going to bias our analysis. So this is a very well-known problem. So many people have already put their heads together to try and figure this out. And I'm not going to go through all of them in this talk, but just simply talk about the one that we found most compelling. This was done by Quentin Baggy and others a few years ago through the means of Bayesian data augmentation. All this means is that we're just, to solve the issue of having these really sharp features that gaps represent in the data, we're just going to complete the data and fill in the gaps. But we have to do so in a statistically consistent way so we don't bias the analysis inadvertently. We do so by creating a distribution that is conditioned on the data that we actually have and use that to fill in the gaps. This is really ideal because we're not touching the data that we actually do have by, say, apodizing, et cetera, and we're optimally mitigating the spectral leakage. However, this is a very expensive operation because it requires multiple matrix operations to repeatedly recompute this distribution. And so what we did, what was novel in our work was to, rather than have this really expensive operation over and over again, we turned it into a proposal. So that's great because now we can eliminate that cost by recomputing this distribution as frequently or infrequently as we like. And even though that we're using sort of like a previous version of the model to draw these fills, we're just letting the data decide what fills are acceptable, using likelihood as the arbiter. This is further appealing because if we choose to make approximations to this distribution to make things even faster, then we're not making any assumptions about the posterior. This is simply assumptions on the proposal and is simply just going to affect its efficiency. And we can further show that we haven't found any evidence that this is going to bias your analysis by looking at the accepted fills. They are properly whitened by the true distribution. And we also ran the analysis on a toy model many, many times and produced a PP plot. So we found that the recovered parameters lied in the x credible interval x fraction of the time. So that shows that there is no, working in this Bayesian setting, there's no evidence of a bias in doing this technique. But we found further uses for this tool, not just for gap filling. We can also do something that we called edge extension with it. So we have, due to the finite length of the data, we also have a spectral leakage on the edges of your data set. And normally you would just apodize them. But we decided we can just treat the edges as just a super long gap and fill them out to some extent, and then chop it off once we eliminate the spectral leakage. So that means that we are not losing any information by smoothing out or tapering the edges, but then we do have to generate new data and transform it. We also found that this method is flexible. So if we have, you can imagine that if after like a maintenance period of a couple of days, the state of the instrument noise is not going to be the same prior to the gap. So you need to have some method that's able to smoothly join the two models, and that's exactly what we did. So we found that even if we have a state change across the gap, say like raising the amplitude of noise, et cetera, then we can still smoothly fill in the hole. This, of course, is limited by our assumption that the noise is not significantly changing, it's locally stationary. I mean, anyone's gonna have a hard time if like over a shorter and shorter gap period that the noise changes more and more significantly. It's just not feasible. Further, we just ran this analysis on a very prototype LISA-like analysis where we just inserted a monochrome sinusoid galactic binary embedded in a simulation of non-stationary LISA noise that has that modulation due to the unresolved galactic foreground component. And we saw that we got parameter recovery consistent with ungapped data. And just to prove that we weren't like inserting, being sneaky and inserting data or that wasn't there, we saw that we actually had a broadening in the posteriors consistent with actually losing information from having gaps in the data. So in summary, we have this efficient way of solving gaps through Bayesian data augmentation, and this is a really appealing tool because it is able to be applied in a very broad sense. It works for any sort of gap pattern. However much data that you lose, if you cut more and more holes in your data, you're just going to be increasing the uncertainty in your fills. You're not biasing the analysis at all. And we also found these additional uses in eliminating edge effects through edge extension and also being able to accommodate significant noise jumps in the noise state. And of course, this is just a general tool. It's applicable to any future observatory that observes long duration signals and over which the noises could change significantly and also has gaps in it. All right, thank you.
Thanks. Several minutes for questions, so go ahead. Hands up. Do we have a microphone? We don't have a mic, people.
So my question is about that initial step that you do, the one-time calculation, and then are able to marginalize on the cheap. Let's say I'm running a global fit on data that has a bunch of gaps in it. It takes a while for that global fit to burn in.
Right.
So do you have to redo that initialization step, the expensive one, while the rest of the global fit is converging?
Right, so ideally, you would start off with maybe some sort of like primitive fill to really just get an initial reduction in the spectral leakage, but then as you're burning in, you can update that as frequently or infrequently as you like, and ideally it should just get better and better. It's just a burn-in process. So yeah, that's something that we haven't experimented too much with. We found that we can actually get a pretty good approximation to the initial state, at least in our toy model, so that we actually landed right in the posterior. But yeah, it's something to still be experimented with, like how frequently you update, et cetera. Yeah.
Okay, that was yours? Okay. Well, I had one, but we can, since I have the mic. While I walk over, I was wondering about for the extension, how far do you go? Since you're extrapolating rather than interpolating, obviously at some point you might be worried about like diverging a little bit.
Right, so it's not like a spline, so it's not like extrapolation. It's simply just a draw from a distribution that's constrained by like the endpoints. So yeah, right. When you have one point that's constrained and one that's not, it's just kind of free to go wherever it wants. But that scale is set by the wavelet kernel size. That just gives like a natural neighborhood to extend out the data. Yeah.
So sometimes you zero fill the data so that you get more points in the spectrum, fill in incremental line shape. Would that affect what you're doing?
I'm sorry, can you ask the question again?
When you have a time series,
Yep.
you add zero somewhere so that you get more points in the spectrum to follow incremental line shape to see where the center of the peak is and so forth in the Fourier analysis. And I just wonder.
Oh, okay. Well, so the gaps that we treated in this prototype analysis, we just treat them as like zeroed data, but we filled them in, so they're not zeros anymore. But like in the likelihood, the gaps basically just are completely kind of subtracted out, so there's no additional information. I don't know if that does that answer your question? We can talk after, yeah.
Just give space for one online question, and then I think we have two additional questions there. Question for Noah: is any of your method dependent on the use of wavelets, or could you apply your imputation approach to data processed using Fourier transform-based methods like overlapped segment averaging?
This is applicable to any basis. The data that we generate to use to fill in the gaps is generated in the time domain, and you can put it in whatever domain you like. We chose the wavelet basis for the reason that the noise is non-stationary, and we also have this fast version of the transform to move it into the wavelet basis. But in principle, you can do it in whatever basis you like, whatever works for you.
How big of a gaps were you considered in your test?
In the tests, we used gaps that were like up to a few days. Yeah. Smallest ones were like a few seconds. Yeah.
Any more questions? If not, thanks, Noah.
Good afternoon, everyone. I'm Chen Haokang from Huazhou University of Science and Technology. My topic today is robust characterization and subtraction of tail-to lines coupling noise for space-based gravitational wave interferometry. And okay, here is my outline. I will organize this talk into 4 parts: TTL noise, background, coefficient, characterization, marginal likelihood subtraction, and CNN-based monitoring. Let me start with the mine data processing challenge. In ground-based detectors, these 2 arms can be nearly equal, so laser frequency noise can largely cancelled. In space, the arms are millions of kilometers long, unequal, and slowly changing. Because of this mismatch, laser frequency noise can't cancel directly and can be much stronger than the gravitational wave signal. So space-based detectors have noise, different noise elements and need a different noise removal method. To make this clear, the next slide shows the mine noise source. This table summarizes the mine noise source. Test mass acceleration noise and short noise set the basic noise floor, and all other noise must be reduced below it. Laser frequency noise is mainly removed by time-delay interferometry or TDI. TTL noise is more difficult because its coupling coefficients depends on the optical setup and the TDI combination. For TTL noise, the question mark means that the subtraction is more difficult. The TTL coupling coefficients we need to estimate accurately. This is and it depends on the TDI combination. So this is why we need to discuss TDI before TTL. TDI removes the largest laser noise and also changes how TTL noise appears in the final data combination. So let me briefly recall the role of TDI. Because the arms are unequal, laser frequency noise can't cancel directly. TDI uses proper time delays to build a virtual equal arm interferometer and shown in the upper part of this slide. These equations below show that delayed phase measurements are combined to cancel laser frequency noise. So after TDI, the largest noise is suppressed, and we can study the remaining noise in TDI outputs, including TTL noise. So physically, TTL coupling means that the angular jitter or lateral motion is converted into the longitudinal measurement. On the left, we can see a Michelson interferometer example. When the measurement beam reflects off a tilted mirror while the reference beam stays fixed, it causes a phase change. The middle expression gives the model of effect, and then we use this model to simulate. The right plot shows why this is matters. After forming TDI combinations, the TTL contribution, you can see the black line, is higher than the noise floor. In the high frequency band, especially above about 20 millihertz, TTL noise can become higher than the noise floor for all TDI combinations. So the conclusion is direct. TTL noise needs to be estimated, then subtracted and monitored. The slide shows our first result, the TTL coefficient scratcher for 45 second generation geometric TDI combinations. In the metric on the left, each row is one TDI combination and each column is one TTL coupling coefficient. The number means that this coefficient appears in that TDI combination. Different TDI combinations use different lengths and time delays, so they contain different TTL information. The space-time diagrams on the right show typical case. The numbers 12, 16, and 24 mean how many TTL coefficients can be resolved. This tells us which coefficients can be estimated in the specific TDI combination. So after we know which coefficients can be estimated, the next question is how to estimate them correctly. Even after optical design and alignment, post-processing is still needed in this figure. There are two main practical problems. First, as shown in this panel, TTL coupling coefficients may slowly change with time. Second, local bursts may appear in the frequency domain. Also, in a real mission, the noise floor is not practically known. A standard least square method can give biased results if the noise model is not correct, or if a burst appears into the data. So we use a marginal likelihood method. In this method, we do not fix the noise flow in advance. Instead, we include the uncertainty of the noise flow in the coefficient estimation. This slide shows our marginal likelihood plus MCMC pipeline. We estimate the TTL coupling coefficients from the TDI data and angular results, while including the uncertainty of the noise flow. This middle panel gives the marginal likelihood function. The key point is that we do not assume the noise spectrum is perfectly known. In the right panel, we can see the coefficient errors are below the 0.1 millimeters per reading requirement. This means the recovered coefficients are accurate enough for TTL noise subtraction. Next, we test whether this method still works when the data contain a local burst in frequency. Here we inject a narrow band burst into the frequency domain. Then we estimate the TTL coefficients again using both least squares and marginal likelihood. The right panel compares the coefficients errors for 45 TDI combinations. Least squares can be biased because it may fit part of the burst and the TTL noise. Marginal likelihood is more stable because it includes the uncertainty of the noise flow, so the burst has the least effect on the coefficient estimation and the residual spectrum stays close to the nominal noise flow. The next part is about the quality of angular measurements. TTL subtraction needs angular results, which is provided by the DWS system. So if the DWS noise becomes high, the angular information becomes noisy, and then the TTL coefficients becomes worse. The lower left panel shows this effect. The error increases with the DWS noise level, but the time frequency diagrams on the right shows that how high noise cases can look very similar to the nominal case. So we need a network to identify bad DWS data before TTL subtraction. This slide shows the CNN plus TDI framework. The CNN is used to check the quality of DWS data. The CNN identifies DWS channels with high rate of noise. Then we avoid these unreliable channels and choose suitable TDI combinations for TTL subtraction. The ROC curve and the configuration matrix shows that this identification works very well. The lower panels shows that even when the DWS noise is increased by factors of 30 at 50, the coefficient errors can stay below 0.1 millimeters per reading. After the CNN identified some DWS channels as too noisy, we do not use the TTL coefficients for the direct subtraction. But we still need to monitor these coefficients. Because they may drift to a dangerous level, the formula on the left estimates the coefficient error from two inputs, the angular jitter level and the DWS readout noise level. The plot on the right is a Monte Carlo test with DWS noise increased by a factor of 30. In this case, the analytical model predicts an RMS error of about 1.36 millimeters per reading. Since the TTL coefficients are expected to lie between about -2 to +2 millimeters per reading, so we can set a wider monitoring range, for example, from -5 to +5 millimeters per reading. So if an estimate coefficient goes outside this range, we flag it as a possible harmful drift. So that's my conclusion. First, we studied TTL coupling in 45 second generation TDI combination and identified which coefficients can be estimated. Second, we developed a marginal likelihood method that includes the uncertainty of the noise flow and gives accurate TTL coefficients recovery. Third, we used CNN-based DWS noise screening together with analytical monitoring to support TTL subtraction when DWS noise becomes high. So finally, I would like to acknowledge my cooperators, Professor Wang Panpan and Professor Shao Chenggang. So thank you for your attention.
Thanks, Haokang. Do we have any questions in the room? Yeah.
Hi, yes, thanks for the talk. I was wondering about the noise burst. You said some local noise burst. Could you explain a little more what channel, what kind of noise you're talking about? Is it a burst of like longitudinal motion, or is it a local, what, and just so I understand how it's traveling through TDI and affecting your measurement.
Okay. For this burst, we do not we just use it for data simulation because we want to test the robustness when we get some burst in the frequency domain. So we do not see it from the factor or the other factor. We just want to test the robustness for our method.
Okay, I see Robbie has a question. Then we can maybe see if we have questions online.
Thanks for the nice talk. I was wondering how much data do you use, and on what time scale do you think the TTL coefficients will be stationary?
Oh, we use the data from 2 days data.
Okay, any more questions? We have time for like one last brief question. Okay, thanks again, Haokang.
Thank you very much.
And our next presentation is another remote presentation. Do we have John Baker online?
All right, so, and Eleonora is one of the collaborators on this work here. But so this is, we just heard a talk about time delay interferometry and some motivation about the necessity of this for reducing laser noise and other kinds, the number of different kinds of noise that even beyond laser noise that it is important to reduce, including the TTL. But here we're just going to be thinking about the simpler problem of data with just laser noise in it. And this is a project we've been working on for a number of years at kind of a low speed, say. But you've seen some description of TDI. It seems important to the entire structure of LISA's design. But maybe there's ways to eliminate some of this kind of common mode modelable sources of noise without TDIs, alternative methods. So, and we're looking at one method like that. So, picture on the upper right here, I can't seem to point with a mouse or something. It just kind of illustrates the amount of noise that we need to contend with is quite large. It's 8 orders of magnitude or so that we need to suppress from just the laser frequency noise. And time delay interferometry works. It's a good system. We're combining the 18 kind of individual interferometry measurements of LISA in a way that eliminates the laser noise, and this has been very well studied over decades now. As was just said, so synthesizing a kind of equal arm interferometer. But there could be other approaches, and maybe in some circumstances another approach could be more robust to some types of marginal circumstances, or if there's something confusing, having a different point of view could be helpful in understanding what's going on. So that's part of the motivation why we're looking at this. So here's a few ideas other than sort of standard TDI that have been kind of thought about. TDI, a little table here on the right. And then I'm kind of in here just considering a few different categories of questions you could ask about your method. Does it require this ranging information? You've heard discussion in Ryan DeRosa's talk, for example, this morning that you need to resolve LISA needs a subsystem to resolve the ranges between the spacecraft to sort of meter level in order to realize the TDI. But maybe some methods don't need that. And so one is TDI ranging, which infers the ranges. And is it local in time, or does it combine data across a wide stretches of time? TDI is semi-local in time, requiring sort of several light crossing times of data to be confined in order to produce one sort of noise-free, laser noise-free data set. And then, is it data-driven, and in what way is it? So the key element of our method is we don't tell it what the correlations are in the noise at all, even in structure. We let the sort of data method figure it out for us. So let's look at what does TDI actually do in order to understand what PCI does. So it's a recombination of a number of different data streams with delays in them, with certain coefficients. And so the delays are not, the data comes in digital units, but the delays are in very precise, continuous amounts of time. So in order to realize that, we can't make a fractional step delay. We have to do some kind of fractional delay filtering here. And so what we really end up with is a sort of different set of coefficients, but still ultimately it is digital data, and there is some set of coefficients which you can think of all the TDI information together with those fractional filtering delay coefficients and all the information about delays that tells you how to construct TDI output channels from the input channels that you have. We also have another, this thinking of it as sort of everything is a constant and the coefficients not depending on time. For TDI, they do have to depend on time. There's another approach we can sort of think about in terms of coefficients when there's time dependence, and if you would like to have a version of a matrix that doesn't have explicit time dependence, you can do a kind of Taylor expansion. But let me leave that off. Well, one thing, sorry, this green box at the bottom here. One thing I wanted to mention is that we realized later that we haven't really addressed the question of whether the method is stationary or close to stationary. Okay. my animations are a little funny here, but so, and our method is instead of, so we have that big matrix that comes from, you could make a sort of recombination of all the input channels with some delays, with some integer delays, and produce some output channels that don't have laser noise. TDI gives you a prescription for how to do that, but what if we skip the prescription and just ask the data, what combination of data is going to be free of noise? And so a simple method like principal component analysis sort of rearranges the data, recombines the linear combinations of the data input streams, and you can then, in sort of quasi-independent units, and then you can look for the ones that have the minimum noise. The usual method where PCI is applied is you're looking for sort of the largest features. In our case, we're looking for the ones with the smallest features, meaning they're free of the laser noise. I need to accelerate myself here. And this, we've looked at this for a few years. It does seem to do the job. It doesn't give you quite the same as TDI. This plot's showing you sort of in terms of sensitivity. This is from a few years ago. You get a great deal of suppression of the laser noise from TDI using our sort of data-driven method. You can still suppress the laser noise to below the other noises, but not nearly as well as what you get with TDI, but enough for practical purposes. One thing that we hadn't asked before, and we just sort of realized recently, is that when we look at this, we didn't actually, so I briefly mentioned that sort of in order for PCI to work better, because the coefficients need to evolve with time, we have a sort of Taylor expansion version of this, but we didn't really ask the Taylor expansion to avoid being non-stationary as much as it can. And so in fact, it's not necessarily non-stationary. And so depending on the sort of order of Taylor expansion, you can get quite a bit of non-stationarity, which is kind of seen in these plots. The right-hand side, the left-hand side is just kind of pictures of the output channels that you get. The right-hand side at the top is kind of standard deviations per channel, and you can, and this sort of across sort of little bin segments of the time data, you can see it's varying in time, and the sort of first order and second order in sort of Taylor expansion, you see you get more variation in time, and at the bottom is the correlations between the different channels. But so now take a jump onto the next part of this presentation. With give you a sort of overview. That's a sort of introduction to what we're talking about, kind of a development. We're doing a very slow sort of development process on this. In the last couple of years, since the last LISA Symposium, we'd already sort of invented this idea. We've sort of cleaned it up in a way that can be developed to closer in analogy with the development going on for TDI. And also TDI infinity is another method that's still being looked at. So we want to like to be able to sort of compare these in apples to apples ways and to look at simulations of LISA the way everybody else is. So we've sort of redeveloped this in a way that's useful. We're now working with simulations coming from directly from LISA instrument like we have in some of the data challenges. And we're in the process of sort of pushing forward with making this, engineering this a bit more. There's a couple questions that are important to look at. And the biggest challenge we have going forward is really, our method is really only looking at like a day or two of data at a time. If you directly apply this sort of PCA approach, you can't really generalize that kind of Taylor series in time-dependent thing to longer stretches of data. So how do we generalize this to longer data is a key question. But first, let me give you a quick peek and show you evidence that we've made a little bit of progress and that we're really working with kind of LISA instrument data the same way as everyone, the same way as it's kind of being standard by most of the people working on kind of LISA data processing stuff now. And I'm going to confess that in everything I showed you before, in fact, what we showed in previous papers and such, is that we kind of cheated before because we didn't take raw sort of LISA phase meter measurement channels as our input for this method. We took so-called sort of single link measurements, which are basically kind of a link all the way from one test mass on one spacecraft to a test mass on the other. And to get those, you actually have to combine multiple interferometry channels, and you have to do it with information of the delays if you want the laser noise to cancel correctly. So we kind of had already baked in a little bit of information about the delays, and we weren't completely avoiding it. In principle, the PCI method, our method, we don't have to work with those synthesized single link channels. We could work with the raw 18 channels, but and the plot on the right is showing you that this actually works now. That's actually from a few days ago. For the first time I was able to make a plot like this. It's not without cost. We find we had to extend the size of the kernel over which we're doing those delay coefficients, the number of looking back in time sort of integer delays you have to combine. And we had to use more output channels, but because we don't just get 3 channels like TDI, we're kind of building sensitivity out of a larger number of channels. And then sort of jumping to another plot here, showing you that if we don't use all that, the plot on the right, the blue curve at the top there is the blue and sort of gold curves are comparing the ADAs, which are the sort of synthesized single link channels, and then the 18 interferometer data channel, which is like really not performing as well if we don't use enough information. Okay, jumping to the next topic, sort of showing you little snippets of kind of where I am in my sort of lab book right now. The next topic is what I was showing you right there was what we see when we're using the LISA simulations with 6 independent sort of lasers and no laser locking scheme. Strangely enough, we turn on the laser locking in the simulation. The PCI data, the PCI result shows this ridiculously orders of magnitude too much sensitivity. And it's a blue curve, moves way down many orders of magnitude below. This can't be real, but it doesn't seem to be just kind of an artifact of our analysis. It seems that somehow the PCI has figured out a way to unwind the locked laser noise, more than just the laser noise, but unwind a large amount of the simulated noise. And a guess is that this is showing us as a kind of lack of sufficient realism in the simulations for what we want. In particular, there's no so-called spacecraft jitter, if I understand right, in the simulations that we're using. They have test mass noise, laser noise, measurement noise, but if you aren't worried about spacecraft jitter, you can just ignore the test mass altogether, and you're not exposed to the acceleration noise, et cetera. So makes sense. The simulations we're looking at weren't really invented for the kind of test, the approach that we're using. PCI was really meant for TDI, and these kind of things maybe are more important for us. That's just, I'm not sure if that's what's going on, but, and then just really quickly, because I see I'm already out of time, extending to longer data, we're trying to do that by, we're doing that first, we're doing that by breaking the data into sort of little chunks like could be a day or hours, and then doing the PCI process for each little chunk and then kind of stitching them together with interpolation. So we're, to develop that, we're doing that first with just TDI structured in the same way as we're doing PCI. So there it's explicit what you need to do at each chunk, but we can combine interpolated versions of the TDI kernels at say, as long as we do them, say, within an hour of each other, and then we add those together to get a kind of interpolated output channels. And why is my, there, oh, it's too much, okay. So the next plot, which is taking a little bit of time materializing here, I think, hopefully it is coming. Come on. All right, so this is noise with different versions of this. If I just use a constant, not evolving in time, TDI kernel, you get the blue curve. And there's way too much noise everywhere except at the exact moment at which the kernel is applied. If you do interpolation with a number of different times, you can bring that noise down. And if you look at, if you do it frequently enough so that you're sampling like roughly every hour, then linear interpolation is enough to get you comfortably below the sort of other noises that you're interested in. And so, summary, we have an alternative here. We've done some work on it. There's a package called PCI-Pi. Sensitivity can be comparable to TDI as long as, in the ways we've looked at it so far, but we're in the middle of a development process trying to make this more realistic and and be able to do things like actually try a Bayesian inference analysis with it.
Thanks, John. We are actually out of time for questions, so unless there is like an extremely brief question, I think we're going to direct you to chat with John offline. Okay? Thank you again, John.
Okay, so speaking from a guy from the Pathfinder era and the Pathfinder Sega, so now we're dealing with LISA and bringing the GRS in LISA. We have to face a lot of challenges, even if the GRS worked perfectly. So when we build the instrument, we put the GRS in the right position, the optical bench, the telescope, and we still have to guarantee a level of acceleration which was achieved already in Pathfinder. But in terms of electrostatics and other things, what you face is that when you have a loss of legacy because you have another industrial partner, you have another team in ESA that you have to face with, that you have to convince, and also because you have some improvements of changes in the design, even small, you sometimes have to rebuild the wheel and start over the modeling and to justify. So in terms of electrostatic, LISA, it's full of electrostatics because it has a fundamental role in different things: sensing position and actuation control forces, determining the stiffness, and influence. It has a strong influence in the test mass charging and accumulation and discharging process. It also is responsible for a charge-induced force on the test mass, so related to that also on the noise floor of the instrument. And like this. So we have to face, we are discussing here the electrostatic model, and then we take our GRS, which is this big, and then we just consider the electrode housing in the test mass. We start to discretize and then go in FEM, in a finite element model, to discretize and try to catch all the details of the design in order to calculate the electric field of inside the gap between the test mass and the electrode housing. Solving numerically so in finite element model the Laplace equation and between the gap of the test mass and the electrode housing. So you end up with a different configuration where with the electric field you can calculate the capacitance between the different part of the GRS, especially from the electrodes with respect to test mass. And then also you can calculate directly the force, electrostatic force and torque that you apply on the test mass when you have applied voltages on the electrodes. And also you can trace the electrons in the test mass gap, solving the electron equation of motion when you have electrons flowing in the gap. So starting from the capacitance model, so what you have a bunch of electrodes that are used for sensing and actuating forces. The electrode have a capacitance directly with respect to test mass, but they also have a capacitance, especially a change of capacitance of the electrode with respect to the grounded housing. And that capacitance, which has a H suffix, it's important for the calculation of the force, and it is fundamental to have a finite model to to get that coefficient. So this is one of the basic reasons you have to build this model in FEM. And with the capacitance model, you can what you do, you can simulate different position of the test mass inside the Gaussian. You can calculate a bunch of capacitance, and so you can extract capacitance derivative expressed as a coefficient of a polynomial fit of all this distribution of capacitance with respect to test mass states. And with that, and first, so you have here a formula where you have capacitance derivative and second derivatives with respect to coefficients and position and rotation of the test masses. So with that, you can inform the facts on where the test mass really is. When you're reading the capacitance, you have to understand where the test mass is. And then with the capacitance model, you can express the force of that you apply on the test mass when you have electrodes applied, voltages applied on electrodes. With that, you can inform what voltages you have to apply to the facts in order to have a given force which is required to stabilize, to center the test mass inside the housing. It is important, especially in test mass release operation. If you expand the force expression to first order, you also have stiffness terms. So what happens when you move the test mass? You have a force which is related to the second derivatives of the capacitance. So that was fundamental to derive a good and complete stiffness model to set the requirements of the GRS. And if you start now to think about, you can use this model also because you can trace the electrons in the gap. This model, it's very important also to determine the performances, the functioning of the discharge process and the discharge system for the LISA test mass. So what you do in general to control the charge on the test mass, which is isolated, so it can accumulate charge over time, you shine different part of the electrode housing and the test mass with the UV light, and with the photoelectrons you produce a bunch of electrons going from and to the test mass. This flow of electrons are driven by the test mass potential, so you have a curve like this, which is an apparent potential curve that basically it's the derivative of the test mass potential as a function of test mass potential, so it's like a phase diagram. And you see that this is a process of the charging which is passively stable. So when you have a mass, when you have a current here which is positive, it means that you are charging the test mass, because the electrons flows from out of the test mass is bigger than the electrons that goes to the test mass, so you have a positive charging, and you go to some equilibrium potential. The same things happen, but vice versa, when you are higher potentials with the test mass, you have that the test mass is more attracting electrons, so you have a current that brings you back to equilibrium. In order to trace the electrons and what they do, you need a FEM, because especially you are illuminating not a planar surface, but you are illuminating areas where the geometry is complicated. You have holes, indents, etc. And in that area, you also have electrodes and voltages. So you have a high gradient region where the flux can change from very close points. So this is important. So with the FEM, you can trace these electrons from these holes and features. And it is fundamental also to extract the end-to-end discharge test if you have in Trento, the torsion pendulum measurements, and also to in the design of and the test of the surface properties of the test mass electrode housing, done to calculate the work function and the emissivity, the quantum yield of the surfaces. This is important to somehow guide the measurements and decide which kind of values you want to look at, you want to see for this parameter when you measure these surface properties. And this is a big diagram of all the electrons that you can trace that are hidden in the holes and the region which are not planar with respect to test mass, that you can reach and see when you have a FEM that allows you to trace them. Okay. This is just for your curiosity a comparison of the model that we did with some torsion pendulum data that we had. You see that with a single model and deciding what kind of emissivity, so quantum yield, work function you have of the surfaces, you see that for different configuration of the measurements, so with pulsed illumination, with applied voltages on the electrode to bias the flux, you see that the model is able to follow the measurements very well. So we just fit one parameter for one of these curves and then propagate the same number for the other curves. So you see that we were very close. And speaking still of the torsion pendulum, okay. You have to consider that you have to customize also the electrostatic model in order to capture some features that you don't have in the GRS of LISA. Especially you have the cross shaft that you have to, that is attached here at the test mat. At some point, you have to model this feature of the design in order to capture the electrostatics here, the capacitance of the test mass with respect to shaft, also, which adds up to the capacity of the test mass with respect to housing, which is important in order to have a close match with the actual design of the torsion pendulum. And then you see here a nice shot of as an example of stiffness measurement that we did with the torsion pendulum and the experimental and the simulation provided that matches at some point to less than 10% with the data measured. And you see if you want to see the poster from Filippo Mazzini, you see the actual measurements of the torsion pendulum. Here we have, 1 minute. Okay, I'll go a little bit fast. So tracing electrons is here interesting also for a test bed we had in Trento with to simulate the charge on the test bed with a proton beam at the facility in Trento, which is we reach energies of 250 MeV. But then I would like to close with the space environment. So it's not an ongoing, it's a starting field that starting things that we are doing here in Trento. So if you imagine that you are charged up with particles in space, with the galactic cosmic rays, you have to also to consider solar energetic particles which are transients. So it goes with a scale of 1 day, with fluxes that can change in an order of 1 or 2 days by order of magnitudes. You see here 2 examples of 2 solar energetic particles events that are occurred in 1 year between 2023 and 2024. A couple of more are in the middle of these times. If you consider you are charged up with these solar particles, 20 to hundreds of times more than the normal flux of the galactic cosmic rays, you see that you have a charge signal. So you are charged, the test mass charged up during this transient, which lasts a couple of hours. And then in general, in this time scale, the discharge system is not able to catch up. So you have a charge that is accumulated, you have a force. And if you calculate, very simply, consider only this one source of signal, you have a not interesting signal to noise values. So those are transient that you actually see on the data of the LISA. With something silly, because a friend that likes solar physics, I couldn't help to think about the black hole sun of Soundgarden when I was playing with this data. Thanks. I would have played that, but I didn't know if I could do it.
Thanks, Valerio. Questions for Valerio in the room? Actually, I have one. So you the data that you were showing before of the test mass illumination were on data that you got from the torsion pendulum, and now you're running simulations on the solar flux to try and see what is going to be the test mass charging coming from the sun, right? Do you, like, are you still in the process of like simulating the data from the sun, or did you already apply that to the model that you have for the test mass charging, for the new electrostatics model of test mass?
So you're speaking about the specifically of the environmental charging from the sun?
Yeah.
Okay. So in general, you have those measurements that you see here are from METIS and METIS, no, in this direction. METIS, you know, this is a proton beam flux, a couple of beams of energies. You have a time series of that, but then you need to simulate that, you know, continuously in order to have, the right profile. In general, what you do, you choose some places where you want to simulate, and then you reconstruct the dynamics from those numbers, okay? And then you apply that, and then you can build the charging curve. Then with the charging curve, you integrate. You calculate the first transformer, you integrate the Fourier transform, and you get the amplitude of the signal. This is more or less what you do. So, yes.
Okay.
Okay.
I don't think we have any online questions. Okay, thank you, Valerio.
Thank you.
And our next presenter is Kohei.
Okay. Hello, I'm Kohei from University of Maryland, Baltimore County, and Goddard Space Flight Center. So today I'm going to talk about observable-based reformulation of time delay interferometry, in which we aim for bridging between actual metrology system and TDI on paper using PRN ranging measurements. So this is a really brief summary of TDI, which maybe I don't need to go through because people already mentioned that, but what's important is we delay phase signals in post-processing to synthesize equal arm interferometer, and our baseline is to provide those delays we use in TDI using PRN ranging. And classically, we write TDI with this kind of diagram, but actual spacecraft is much more than single dot. And once we consider internal structure of spacecraft, the delay we need to apply is also a little bit unclear. So let me try to explain what kind of delay we really need to apply in TDI and how we can get it from ranging measurement. So here I'm showing the laser trace, so one of the laser traces. And the laser goes to the distant spacecraft, goes to distant spacecraft, and its phase is extracted by phase meter. It also couples to the local phase measurement system as a local oscillator beam. And we want to remove, for example, this instantaneous feature of the laser frequency noise. So what we really need to suppress laser noise is this path. So green minus cyan. Because at the end of the day, what we have are data files in which phase signals are time-stamped. So if we have the delay of the timestamp between this phase measurement system to this phase measurement system, we can suppress laser noise. How can we get it with PRN ranging signals? So now I'm showing the PRN ranging signal trace. So it is generated here, and it modulates the beam phase. And one goes to distant spacecraft, and delay is extracted. But we also have this local ranging measurement to monitor the local delay. If we advance this phase measurement with this local delay, then we can advance the phase signals here to PRN generation time. Then we can delay to the distant spacecraft. So what happened? So yellow delays here are canceled between advancement and delay because they are identical in these two phase measurements, delay measurement. We also have these extra delays in ranging measurement, purple, but they are all digital delays inside the FPGA, and they are very easy to remove. So let me just assume that it has been already removed from our ranging measurement. Then what's left is really cyan and green, which is what we need to suppress laser noise. So 2 takeaways so far. One is advancement delay pair of ranging measurement provides you what TDI needs to suppress laser noise. 2, this idea is actually, this idea can be generalized to all interferometers in TDI, including reference and test mass interferometers, because they are all based on same measurement principle called heterodyne interferometry. So let me take one step back. So what was the problem? So spacecraft is more than a single dot. So actual metrology system is much more complex than a single dot. So our goal is to recover point mass spacecraft framework using ranging measurement. Then we can just perform TDI as people normally do. And here is a diagram, and the notation of the diagram I normally use to represent metrology system. So you don't need to remember those operators. What's important is those markers. So PRN is generated at the empty square, and it modulates a beam at the empty circle, which also is a definition of photon generation for me. And they go to interference point, field circle, or beam splitter in our case, and they go to measurement, represented by field square. I keep showing this notation for the rest of the presentation. So let's go through the algorithm of TDI. So TDI has several intermediary steps. The first step is so-called Guzai variable, in which we need to remove relative displacement noise between OB and test mass. And for the purpose, we need to combine reference and test mass interferometer with interspacecraft interferometer. And here, we need to apply some delays to cancel the adverse effect of onboard delays. You don't need to remember the equation, but what conceptually happens is shown on the right. We first advance test mass and reference interferometers to the PRN generation point and delay it to interspacecraft interferometer. In this way, we can synchronize all the interferometers. And we confirm that this successfully cancels the adverse effect of onboard delays, and we could achieve also the cancellation of OB test mass displacement noise. And step 2 is eta variable. So this is interspacecraft test mass to test mass phase measurement with only left lasers. So at the end, we want to write down everything based on left lasers. And for the purpose, we need to remove laser frequency noise of the right system. And for the purpose, we need to combine reference interferometers with Guzai variable. Again, you don't need to remember equation, but what happens is we first advance reference interferometers to associated PRN generation point, then delay it to Guzai variable measurement time. In this way, we can, again, cancel the onboard delay effect and remove right laser noise. So now we only have 8 markers per spacecraft. And we also need operators connecting eta variables because we want to perform TDI. So we check that we can generate these 2 operators, D and T. And D is connecting distant eta variables. So if you are familiar with TDI, maybe this is the most intuitive operator for you because this is connecting distant eta variables. And we can, but the difference here is we can construct D operator only from onboard PRN ranging measurement. So D operator connects distant eta variables. And we also can construct T operator connecting, connecting 2 eta variables on the same spacecraft. So now we have eta variables and operators connecting eta variables. So it seems that we are ready to perform actual TDI combinations. And in the paper, we we did it for TDI-X combination, but these days I was thinking of the generalization of the scheme to arbitrary TDI combinations, and I found that we should have a little bit better physical interpretation of this system. So let me share my latest physical interpretation of what's really going on in this scheme. And for the purpose, I reformulated eta variables, eta ij and ik. And for example, for eta ij, phi jk is the signal beam, and phi ij is the local beam. And these colored are all operators operators apply to phi jk. And so let's look at phi jk. So it's first advanced to Pearson generation point, then it is delayed to associated local eta measurement time by pink, and blue send it to adjacent eta measurement time, and red send it to the distant eta ij measurement time. So this is what happens to signal beam in eta ij. Local oscillator beam, phi ij, it is advanced first to Pearson generation point and delayed to eta ij. And phi jk and phi ij interfere. This is what happens to eta ij beams. And for eta ik, they are almost same. So signal beam phi ki first advanced to Pearson generation, delayed, and sent to the distant eta ik measurement time. And for local oscillator beam, same phi ij, it's first advanced, delayed, but sent to the adjacent eta ik measurement time. So this is what's happening inside the eta variables in this scheme. And our goal is to recover point mass spacecraft framework using this scheme so that people can perform TDI as people normally do. So let's redefine quantities and operators. First, let's redefine beam, because the beams in the eta variable always first have this advancement operator, which means we shift the definition or generation of the photon to the generation of PRN. And we redefine it as phi bar. But we can even redefine it further because they all have these pink operators as well, which means we redefine the beam generation at the time of the measurement, and we call it phi hat. Let's even redefine eta variables. So eta ij is already on the left system, but eta ik is still on the right system, and we want to write everything based on the left system. So let's redefine it, which means we define the right eta variables at the same time of the left eta variables. And we call them eta bar, sorry. And finally, let's even redefine operators to let them connect left to left, which means we combine the blue and red operators and redefine it as a single delay operator, and let's call it d bar. And now everything is written based on left system, so we don't need right markers. So this is, at the end, our spacecraft in this system. And this eta bar is written based on these redefined quantities, operators. And this, if you are familiar with TDI, this is exactly the same algebraic structure as normal TDI formulation. So you can just perform TDI based on this eta bar and d bar. And I'm not sure if even the people from AEI are aware of that, but the key idea behind this is already demonstrated at the AEI. So if you are interested, you can also read this paper, I guess. And here is a summary, but let me just stop speaking here. Thank you.
Questions for Kohei? Daniel?
Quick question. Thanks for all, very clear. But there is something I didn't get exactly. So these delays, these additional delays that are due to the electronics and the thing on board the spacecraft, you have to calibrate on board of the spacecraft when the mission is there before applying those?
No.
It's known. They are known. Then
So what's important here is we consider those onboard delays as integral part of TDI. So what we really need to suppress laser noise is only this, and these additional onboard delays are fully canceled in this pair. But there is only one delay we need to subtract from phase measurement signal, which is purple, because our beam doesn't experience this delay. However, these are digital, and it is very easy to know what this is, because as long as you know what's going on inside the FPGA.
okay, so the PRN measure exactly that one that you are assuming there, apart from the purple one.
Exactly.
Okay, I see. Okay, thanks.
We have time, I think, for another brief question, if someone has one. Yeah, Robbie?
Thanks for the nice talk. So if I understand right, this is kind of a necessary thing to do to take into account the small internal delays, right? Or else when your TTI is not well defined, you'll get you won't cancel things very well. Is that right?
Yes.
And that works in the hexagon data also?
At least in the hexagon, yes.
Oh, nice.
Which doesn't have long arm entity,
right.
But at least hexagon can already simulate a lot of onboard delays, which is the important part of this scheme. So I think the result was promising. Yep.
Very nice.
Thanks, Kohei. The last presenter of this session is Reid.
All right, won't waste any time. There's a footy match on soon. So, no, go back. So my colleagues and I at the Albert Einstein Institute in Hanover have been developing a hardware test bed for the long arm interferometry in LISA to demonstrate TDI in a laboratory environment. So this TDI basically can rush right through it. After that last talk, you measure noise at 2 different points in time, and you shift one backwards in time to cancel them out, and it requires knowledge of your delays to an accuracy of 3 nanoseconds. So that saves a lot of time. So we're building a hardware test bed, and to motivate that, I want to compare it to some of the software simulations that we have already in cases like LISA node, or the very, very vast diagram that Nora showed, or I don't think it was Nora. But so in software, you can basically control very, very carefully every single thing that you put into your simulation framework. And you're relying on the accuracy of your noise models. But in hardware, you have real things not behaving exactly the way that you want them to. And that provides us with enough motivation to try to build something that gives you a full chain test of your L0 data production. We don't want to replace software simulation, but we do want to complement it with something that can reproduce LISA, or parts of LISA in a laboratory environment. Here's an example of one of those pesky instrumentation noise things where an imperfect clock imprints a phase shift in your measured signal. So the concept for our test bed, we're looking at what kind of things we want to reproduce in LISA. So the things that we're looking at to reproduce are the megahertz beat notes between the spacecraft lasers, time-varying 8-second delay, and the signals that are exchanged between the spacecraft are Doppler shifted. They're imprinted with clock sidebands to imprint the time base of one spacecraft onto the measurements so that it can rescale the measurements on another spacecraft to have everything in common time. And then hopefully there will be some gravitational wave modulation on those arms. And the key beat notes are formed at these blue beam splitters here, and they produce what I'll refer to as the eta and zeta variables, which are the inter-spacecraft science measurements, the carrier beat note, and the sideband beat note that carries your timing information. So our testbed platform is a radio frequency system on chip FPGA board, an eval kit built by Xilinx. It's sampled at 125 megahertz, so instead of terahertz carriers, we only have megahertz carriers. But we are able to create LISA-like delays between start and end point of a signal. We can imprint Doppler shifting and gravitational wave injection, and this is actuated via a very convenient Jupyter environment running on the chip, where you can add all of the modulation and actuation that you'd like. And instead of EOMs, we have some electronic clock modulation, and the key interference happens actually on chip in these blue mixers, which is basically just subtraction. And the whole idea is that you have these TDI-compatible outputs that you can measure with a real phase meter, and optionally you have some unmixed outputs for diagnostics and testing. So this is a little bit of an overview of the guts of the FPGA. I'm not going to get into too much detail here, but the main ideas here are that at first an ADC samples your input signal, and PLLs grab an instantaneous frequency value of that signal as a fraction of the clock. These are then delayed for a programmable amount of time, so you input your initial delay and the rate of change of the delay, and that actuates the rate at which memory is requested and then regenerated at the DAC. So, you can inject any manner of superposition of gravitational waves onto this traveling signal as a fractional frequency offset of the data that's in the chip, and then all of this gets resynthesized at the DAC and sent on to a phase meter. So how well does this thing work? So to test that, you take a signal, you split it into two, and you delay one, and you measure the other directly. And the whole idea is to check whether or not this residual actually goes to zero. So if you have your physically delayed signal, and can you shift your undelayed signal back in time, or forward in time rather, so that they cancel out. And kinda. So as you can see, they have a very, very similar noise spectrum, so that means the amplitude is pretty well reproduced, but there is some phase shifting that makes your residual, not zero. And this shows this very common 1 minus delay transfer function, so that gives a good hint on where it comes from. And the benchmark we're using here isn't the usual 1 picometer benchmark, but rather just sort of the inner spacecraft interferometer noise sources to compare where we are with what's actually going to be in the LISA satellites. So that noise that's imprinted with this 1 minus delay transfer function means that it's a noise that's the same, that's having an effect at 2 different times at the signal. So the same clock is driving both the ADC and the DAC, so it's the same noise that's imprinted at 2 different times, once when the signal is sampled by the delay board and once when it's regenerated. And it's the same effect that I showed earlier with this phase dispersion in the digital domain. So we can measure it and remove it. And to do that, we generate a signal on the board and superimpose it onto the output, and that, when it leaves the board, will pick up the timing jitter of the DAC, which is equivalent to the timing jitter of the ADC, because they're driven by the same clock. And you build this correction term, and there you can bring your residual down to below the benchmark that we wanted. But the ranging tone is still there, and I think that's actually because the DDS tone gets some crosstalk from the superposition. So the dynamic delays, so in time-changing delays, we obviously want to do a non-static arms in space. If we had static arms in space, we wouldn't need all of this. So I did a little test where I programmed it to shift by 100 nanoseconds per second for 20 hours. And the blue dots are estimates of the delay using the 1 hertz ranging tone once per hour for about a minute on either side of that hour mark, and the result is it agrees pretty well with what we'd expect. So now let's get to the TDI stuff. So for a TDI test, we can program a board with 2, can I get rid of this? Can I? Move this. So we can program a board with 2 delay lines on it, and we treat each one as a round trip. So it's like putting a giant mirror in space and reflecting all of the light that you're sending out to the distant spacecraft back to your local spacecraft. And there we can construct our ADA observables in post-processing by taking that undelayed signal path from before and just subtracting the phase measurements directly. And now this is not working. There we go. So the X1, the static arm X1 combination reduces to this when you have perfect transponders. And here you can see the noise of these ADA observables as these jagged lines in the X1 combination is pretty dang flat. But we are unable to use the DDS correction that I mentioned in the baseline measurement before because we just don't have enough phase meter channels to run it, but we will soon, so we're going to repeat these measurements with that. But even still, without that correction, which gives us this 1 minus delay transfer function behavior, we're still able to remove 10 orders of magnitude of noise. So then we want to try injecting a gravitational wave. And to do that in our platform, you can build a dictionary of source parameters and then feed it into the LISA Data Challenge waveform package, and then use the GW response libraries to scale it to whatever arms you want. So you can input orbits from that and give it to the GW response package along with the waveform, and it'll give you your D0, your initial delay, your D dot, your D double dot, and then the gravitational response is the fractional frequency shift. You put that into the Jupyter server, and then that gets fed into the delay lines. So for the static test, we are not actually going to use the orbits. We're just going to leave it static and see if the X1 works. And it does. You can see that the signal is buried in the noise of the ADAs, but it is revealed in the TDI combination if you zoom in far enough. So if you zoom in around here, you see the in-spiral phase of this coalescence. This was a massive binary black hole merger. And this orange line is the pre-generated text file relative frequency shift that's just scaled by the TDI combination, and it lines up with the data perfectly. And if you zoom in over here, you see the coalescence time, and if you subtract the injected orange line from the measured blue line, you get a fairly white-looking noise floor. In fact, it's the same noise floor that we saw before with the static non-injection measurement. And so for more noise hunting, we're looking at basically what's limiting our setup right now. Python simulations of our setup show that the strongest contributors are from our delay mismatch, so everything else kind of sits down near the ideal X1 range. But it says our Python simulations are showing us that if we don't know our delays very well, already by a few microseconds it blows up by orders of magnitude. But the delays are constant, or so we think. But the clocks themselves seem to be drifting by microseconds over the course of a measurement. So we took 3 such boards where we took a clock output of each board and compared it with the rubidium standard that's that our phase meters are locked to. And we take the frequency measurement and the phase measurement and use that to calculate a timing drift. And you see that it tends to walk around, and it's correlated, so it's probably temperature driven, but again, it's way above that 3 nanosecond level that we need. And the clock noise then couples in 2 different ways. So firstly, I'm not going to go through all the math, but the clock drift is delay drift. The delay line boards count the delay in clock cycles, so if the time that one clock cycle takes changes, then the macroscopic delay will also change. And if you go through a bit of math, you find that this effect is maximal at Fourier frequencies that are equivalent around 1 over the delay time. Additionally, you get a fractional shift in the frequency due to the fact that the signal frequency is stored as fractions of the clock frequency. So this is just some binary value, and when the clock frequency changes at some time later, you have this fractional change difference that rescales your input frequency when it's regenerated again. So doing some more math, we find that the timing noise between the delay line board and the phase meter must satisfy the following requirements to meet the benchmark performance that I mentioned before. We need 2,000 picoseconds, 2 nanoseconds at low frequencies, or 0.4 picoseconds at around a hertz. And so that just kind of gives us something to aim for in our clock stability. And I think I've made pretty good time. So the conclusions that I'd like to point out is that this testbed is valid as a test platform for TDI, particularly in new algorithms like the one that was mentioned earlier, this PCI construction. But we can inject arbitrary gravitational waves, and we can implement LISA-like signal travel times of real signals. And right now, the hardware limitations aren't necessarily deal breakers. We just need more phase meter channels to do our clock correction, and we need better clocking stability for our noise floor. So the next steps are to overcome our hardware limitations. We're going to put some more advanced phase meter firmware on our lab devices with Moku local compile, but that's currently held up in export control, and repeat those DDS measurements, or repeat those measurements with DDS correction. And then we're going to look at our evaluation kit and see if we can improve the clock locking stability to external references. And then the next steps after that are to refine the tests with multiple delay boards and phase meters and move towards a full constellation simulator with TDI2, full realistic orbital simulations and delay times. And then my colleague will be speaking about moving from a fully electronic setup to a hybrid optical setup with cavity-stabilized lasers as our signal generators, which is more LISA-like, and EOM is for clocking transfer between the simulated spacecraft. That's all I have.
Thank you, Reid. Questions in the room for Reid? Holly.
Great talk, thank you. I have two questions, and I guess my first question is because you're on this slide. Do you think that the implementing like the EOM and the optical setup will help with the clock drift?
We have some ideas about what to use as our clocking source. So there has been one idea floated where you use the signal that you use to actually modulate the clock tone onto the laser as the driving tone also for your measurement. So then they automatically compensate for each other. So you're basically transmitting exactly your measurement time to the other board instead of some external oscillator. But yeah, these are the kind of things that we can test. Like
Very
what's
cool.
the best way to do it? Yeah.
Excellent. And then I can give my microphone if someone else has a question, or I have one more. So in your setup, you showed that you have the two mixers on the same RF board.
Yeah.
Is that realistic, or are you going to have some additional noise suppressed because they're kind of common?
So the point of having the two incoming signals on the same board instead of more of a bidirectional topology is that the values here that you imprint onto your delayed signals are calculated in the rest frame of this spacecraft. So it's in this time, in the time frame of this simulated spacecraft.
Thank you.
Any more questions in the room? Anything online? Okay, thanks. Reid again. And this is the end of this session, so I think there's a break now.